All right, so yeah, I have written Green's theorem, the statement of it here. Positively oriented, piecewise smooth, simple closed curve, D is region closed, and then conclusion there. All right, so the one thing we haven't talked about in this theorem, well, the first thing we haven't talked about besides the conclusion, is positively oriented. So C is a closed curve, simple closed curve, piecewise smooth. Okay, so it simple closed curve. All right, so yeah, we talked about simple and closed last time. Simple but closed is hopefully obvious there to you. It starts at the one point and then it finishes up at the same point. Same initial, same terminal. Simple just means it's not crossing itself, doesn't intersect itself. So we talked about those, and piecewise smooth. Positively oriented, okay, so that means, here's what positively oriented means. So let me just kind of draw one here. So let's say, no matter where I start, it's kind of a loop. So I start here, and then I go around, and it doesn't cross itself. It can do whatever it wants to, but it never crosses itself, and then it comes back there. Okay, so that obviously is piecewise smooth, simple, closed, all those good things. Positively oriented means we're going counterclockwise. You know, kind of like polar, you know, in polar positive angles go counterclockwise. Same, I guess same kind of idea. So that's our example for C, and then D is the region enclosed by the curve. So D is the inside part of that. Okay, so that's what you begin with. All right, so we're doing a line integral over C, and it's P dx plus Q dy, some of the same sort of integrals we saw, but this little symbol right here, okay, so what that symbol means, that symbol means that it's satisfying the premises here of Green's theorem. So the little symbol just kind of a closed circle, a little circle there. So that's all that means. So it's a line integral. That little extra symbol just means that it satisfies the conclusion, the premises there, conditions. Okay, now notice what this says though. So we've got, this is integrating a line integral, but what is this over here? Well, that's just a double integral. All right, so we kind of related a line integral to a double integral, which is different. So this is double integral D, and of course this is how you have to set it up, and then dA. So dA here, double integrals we can integrate with respect to the Cartesian coordinates, x's and y's. We can integrate it with respect to polar coordinates. We can use r's and thetas. So anyway, kind of a neat little result there. We're not going to prove that right here, but just kind of do a couple of examples using it, and make a couple other notes, like, again, what this is useful for is, sometimes this is maybe maybe not difficult. The one we're going to show is not difficult to just do the line integral, but it is, turns out it's going to be easier doing a double integral. So it's just kind of interesting. Line integral equals a double integral. Okay. So let's use Green's theorem to evaluate this one. It is the line integral xy dx plus x squared y cubed dy. Where C, oh, that's over C, where C is triangle of line segments from 0, 0 to 1, 0. And then from that to 1, 2. And then from that into 0, 0, back to 0, 0. So we start at 0, 0. So here's our C. Start at 0, 0. Go to 1, 0. Go to 1, 0. Then we go to 1, 2. And then we go back to 0, 0. Okay. So yeah, we got that positive oriented little curve, all right? So again, we're going to use Green's theorem to do this, and to use Green's theorem, yeah, what we need to do is convert that over to a double integral over d, and so again, d then is just, we've got to figure out what d is. D is the inside of that triangle. So how could I represent that in some useful terms there? Well, obviously, it's not going to be a polar curve. Probably not. Would be the easiest. Probably in this case, the easiest thing to do is just do it in terms of x and y, Cartesian. So, what are my restraints, if you will, on my x's and y's? Well, let's just do the y's here first. The y's would just, if I start with them, they would go from y equals 0 up to this line, which that line in terms of x, what would be the y equals mx plus b for that? Well, the b is 0, the slope, rise 2, run 1, so however you need to. That line right there is y equals 2x. So y would range from 0 to 2x, and then the x just runs 0 to 1. That would cover D. Everybody okay on that? All right. Okay, so our line interval then for C, xy dx plus x squared y cubed dy by Green's theorem equals a double integral over this d right here, partial of q with respect to x minus partial of p with respect to y dA. So I've got my d, and we've kind of got it set up. We integrate then the y's first. So it'd be 0 to 2x for the y's, and then 0 to 1 for the x's. All right, partial of q with respect to x. So out of these two, again, on the line integral, the first one is p, and the second one is q. So we're actually, and this is sort of like proving something is conservative, right? On the q, we take the partial with respect to x, because it's the same thing. So this is p, this is q, and so the partial of q with respect to x would just be 2xy cubed, right? Minus the partial of p with respect to y, well, here's p. So with respect to y, the partial is just x. With me so far? And then dA, we already said dA, we're just going to do dy and then dx. So is that okay? It's not terrible, bad. All right, well, guess it's a double integral, so no telling what you run into, but this one doesn't look too bad, does it? The first one we do is integral with respect to y. So what would that be? Y to the fourth, so it'd be divided by 4 1/2 x y to the fourth minus, and we're integrate with respect to y, so it'd just be xy. And then go 0 to 2x there, and we'll do our x's. So these going for y, so we have 1/2 x, and then 2x to the fourth minus x times 2x. And the zeros give you 0. So you got 1/2 x, 16x to the fourth, so I believe that's going to be half of 16 would be 8 x to the fifth minus 2x cubed dx, which is 8/6 x to the sixth minus 1/2 x to the fourth, and that's going 0 to 1. That's going to be 4/3 minus 1/2, which is let's see, 8. Oh, I need 6 anyway. I did it right. That's not what I should be getting. Okay, what did I do wrong? Oh, right here. 2x squared. That would be, yeah, all right. Next, 2/3. Yeah, 2/3 x cubed. So it's 4/3 minus 2/3. Yes, that's better. More expected. Okay. All right. Okay. Well, yeah. So that's doing it via Green's theorem. And to save a little time, I just copied off. I worked this same line integral right here, using the same little triangle there. I worked it out the direct method, and you can work all the way through it if you want. But so doing it the direct method, notice what that means is you got to do three different parts. You got to do C1, C2, C3. So if we're going to do this line integral like a line integral, you got to do 3 parts. C1, C2, C3. And then, yeah, you have to figure out, well, what's C1 in terms, basically in terms of parametric equations. And I've got them there. C2, C3, same thing. So you got to figure those out. And then you do the integral for each one of those. So you're doing 3 integrals. And it turned out, well, the first one turned out to be 0, so actually wound up just being 2. But anyway, comparing these two, it's not much different. I mean, we wind up with 2/3 again, so it kind of verifies that this works. But anyway, just kind of interesting to see that, yeah, you can do a line integral by 2 by doing a double integral. Any questions on that particular? I'm going to show you one more because it uses polar. Does that look okay? Question or concern? All right, so the other one, real quick, let's do here. Evaluate the line integral over C, y cubed dx minus x cubed dy, where C is a circle of radius 2, centered at the origin. Okay, fairly simple. C there. So obviously that's closed. You got a circle. Radius 2. Okay, so again, use, I did say, use Green's theorem. Yeah, so in this particular case, so D is the region inside that then. And since our double integral, so we're setting this equal to the double integral over that D. Partial of Q with respect to X minus partial of P with respect to Y. A. Yeah, like I said on the first problem there, yeah, we can use, again, Cartesian for dA, or we can use polar. And polar makes real good sense here because if I use Cartesian, I would have to go, if I did the y's first, I'd have to go from this semicircle up to that semicircle. So you got some square roots, and that always is good to avoid if we can. But so yeah, D here in terms of X's and R's and theta is polar. So R, obviously R goes from, we can just do it 0 to 2. And then the thetas very easily are 0, go all the way around, so 0 to 2 pi. So that would sweep out that whole area, right? R goes 0 to 2, and then theta goes 0, so we're sweeping that whole thing out. All right, now, so again, what you have to watch out on this part of it, all right, so the partial of Q with respect to that. So Q is this one. Well, you've got to include the negative. Q is negative x cubed. And P is y cubed. So what's your negative sign there? So the partial of Q with respect to x would be negative 3x squared. Minus the partial of P with respect to y would be minus 3y squared. And then dA. All right, so nothing else. We're reviewing when we go to polar here what we do for dA. Yeah, it's dr d theta, but what else? R dr d theta, yeah. And so yeah, we usually do the r's first, so that's 0 to 2, and then theta is 0 to 2 pi. So to actually evaluate this then, of course we're doing it in polar, so we need to write that in polar. It's not that bad because if you factor off the negative 3, look at what you wind up with. And what, so you get negative 3 times x squared plus y squared. What is x squared plus y squared? That equal r squared. And so come to find out it's actually a pretty easy double integral. So you just have, so you do the r's first. Oh, that'd be r cubed. So it'd be negative 3 times 1/4 r to the 4th. And we're doing that from 0 to 2. So that's what? Negative 3/4, 6 times 16 minus 0. So that's negative 12, so that's negative 12. Theta is just a constant there. And then that goes from 0 to 2 pi, so that's going to be negative 24 pi. So. Question or concern?